Thank you very much. This is joint work with two of my students from Erlangen, as well as Alysson Bessani from Lisbon and Flavio Junqueira from Microsoft. Today's data centers run large-scale distributed applications in which potentially a huge number of processes cooperate to provide a common service. For example, distributed file system like HDFS or distributed data processing framework like MapReduce. Now, whenever multiple processes cooperate, there's usually some form of coordination mechanism required. For example, to elect a leader or to have a distributed queue which allows different processes to communicate. Now, from an application programmer's perspective, the fact that you know how to write a distributed file system does not automatically know that you also know how to correctly and efficiently implement a distributed leader election algorithm, for example. So it turns out to be a good idea to let application programmers focus on the work they know best, for example, the distributed file system, and free them from the need to implement coordination mechanisms. And one way to do this is to use an external coordination service. Now, we've already heard about ZooKeeper. There are plenty other coordination services available, Chubby, DepSpace, only to name a few. Despite the differences, they all share this common approach of not directly implementing all kinds of coordination mechanisms, but instead to provide a small set of very generic functions, which is also called a coordination kernel, maybe some methods for small data storage, maybe one or two synchronization primitives. So to have this small set of functions, which would then allow a client to build more complex abstractions at the client by using these functions. Now, let's take a look at how this works in ZooKeeper. ZooKeeper stores data in nodes in a file system like data tree and provides some generic functions to create those nodes, set the data of those nodes, read the data from those nodes, delete those nodes, so you have your typical CRUD operations. And in addition to that, there's only a small set of additional functions to manage access control, to check whether a node exists or not, and there's this getChildren call, which, for example, allows you to retrieve the names of child nodes. So, for example, if you call this getChildren on this dir node, you would get A, B, and C. So, as I said, a small set of functions, very generic. Let's take a look at how you build more complex abstractions on top of that, using the distributed queue as an example. So, the implementation of the distributed queue here has two functions. An insert function that allows the client to add an element to the queue, and a remove operation which allows the client to remove the current head element from the queue. So as we see here, the insert method is rather simple. All it does is it creates a node in the coordination service, assigns the data to it. Now what the sequential flag here does is it tells ZooKeeper to not only create the node with a specific name, but to add a sequence number which is automatically increased to the node name. So the first time we call this insert method, it will create a node 1, and if we call this multiple times, we end up with nodes 1 through 4, for example. The sequence number automatically increases. We've seen the insert method is rather straightforward, only a single remote call. The complexity is part of the remove operation. Because in order to be able to remove the head element of the queue, what the client first has to do is it has to identify this element. So the way this works in ZooKeeper is the client takes this getChildren call in order to learn all the node names. And using the sequence number encoded in these names, the client is able to detect the head of the queue, which is the node with the lowest sequence number. So in this case, it is node 1. So having found this head element, the client is able to get the data by calling the method on the coordination service, and then finally to remove the head element by using delete. So we see that surrounding the last two statements, there's this for loop, and this is required because there may be scenarios where two or more clients can can call the remove function concurrently. And there may be scenarios in which two clients call this getChildren concurrently, which means they download the same list of nodes, which means they identify the same node as current head element, which means they try to delete the same node. So in these cases, ZooKeeper ensures that only one of the clients will actually be successful. So this is the client which gets a confirmation from ZooKeeper, okay, the node is deleted, and this is a client which is actually able to successfully complete its remove operation. The other client will get an exception from ZooKeeper saying the node you're trying to delete does no longer exist, and this is a signal to the client to enter this for loop once more and to try with the next element. So we've seen a first drawback of this kind of implementation. There may be retries, multiple retries, until we're actually successful to remove an element. Another drawback of this solution can be identified just by looking at the code. Even in the best case, we need 3 remote calls from the client to the service in order to remove even a single element, which is not optimal in terms of latency. Now, let's take a look at how this translates to throughput. What we did was we ran an experiment where we had clients continuously adding an element to the queue, removing an element from the queue, adding an element from the queue, removing, and so on. And here's the results in terms of throughput, so higher is better. For a single client, the queue achieves the throughput of a little over 200 elements per second. The throughput increases with more clients to just under 800 elements per second, but then adding more clients, it decreases. And the reason for that is with more and more clients, we have more and more concurrency. The success rate of the delete operation will drop dramatically, so reaching 2% for 50 clients. And this is why the throughput drops. The problem here is the coordination service, in this case ZooKeeper, still has to perform all those operations, but fewer and fewer clients actually are able to make progress. And again, this is a consequence of this general approach to have this small set of generic functions and to build more complex abstractions at the client. Now, we further investigated this problem. We looked at different coordination mechanisms. We looked at different coordination services. And it turns out this is not a problem specific to distributed queues, and it is not a problem specific to ZooKeeper. In contrast, it is a problem of the fact that there is no small one-fits-all coordination kernel that would allow several or all kinds of coordination mechanisms to be efficiently implemented at the client. Now, what can we do about it? There are basically 2 possible solutions. First, what we can do is we can add new functions to the kernel. For example, if we had a queue remove operation in ZooKeeper, we probably would be able to implement it in a kind or in a way that we achieve good performance. But the problem is with more and more functions, the kernel gets more complex, makes it harder to maintain. So we actually don't want to do that. Another alternative solution would be to have dedicated coordination services for all kinds of coordination mechanisms. This would have the benefit of being able to optimize for certain data structures. So, for example, we could optimize a coordination service for distributed queues. But the downside here would be, instead of having a single coordination service in the data center, we would now end up with multiple coordination services. So this also makes it harder to maintain, and there are high development costs. So our approach is different. What we did was we made the coordination service extensible. And by that we mean a client is able to write custom operations, to register them at the service, to invoke them as long as it needs them, and after the client so when the client does not need them any longer, the custom operations are removed. And this way we would get the best of both worlds. We would still have a small coordination kernel, but we would achieve, or we will achieve good performance due to executing most of the stuff at the server. So in the rest of my talk, I'm first going to talk a little bit more about what are coordination service extensions, show an example of how such an extension might look like. I will go into a little bit more into detail on how to make existing coordination services extensible, and at the end I will briefly present some evaluation results. Now, in a nutshell, what is a coordination service extension? It is a sequence of regular coordination service operations plus a little bit of glue code that are executed atomically at the server side. Now, what is important here is that an extension is not a means to run arbitrary code at the server side. So we want an extension to be a composition of coordination service operations. Extensions come in one of 2 flavors: event extensions and operation extensions. An event extension is a means to customize the reaction of the coordination service to certain events. I won't go into detail for this kind of extension, so please refer to the paper for an example. I will focus on following on the other type of extension, the operation extension, which is triggered by a client request and which basically overrides the regular operation of the coordination service for a certain node. So using such an operation extension, we, for example, can refine the distributed queue implementation. Now, before we actually look at the extension, let's take first a look at how a client uses such an extension. As we see here, we have the exact same methods as before. In fact, the insert method has not changed at all. It is exactly the same as in the regular implementation. However, the remove operation has changed dramatically. So instead of doing all those steps, all the client does in this case is to invoke the get data operation on a node slash queue slash next. And when this operation returns, the client will have the data and the current head element of the queue will have been removed. So how does this work at the server? The first difference we notice is that an extension, in contrast to a client, is able to locally access the coordination server state. So we don't need remote calls anymore. All calls to the state from an extension are local. So that's good in terms of performance. Now, in this case, as I said, the extension is triggered when someone calls get data on this node next. And what the extension does is it performs basically the same steps as the client has done in the regular implementation. And this makes it easy for programmers who know how to write know how to write abstractions for a certain coordination service to also implement extensions for this very same coordination service. So in this case, what the extension does is it tries to, or it identifies the first element in the queue by looking at the sequence numbers, and as soon as the extension has found this, it gets the data, deletes the node, and returns the data. The big difference is we don't need a for loop because all those steps are executed atomically, so there are no retries necessary if we have elements in the queue. So that's a good thing. Another benefit I also mentioned, the client only needs a single remote call to actually remove an element. So no more 3 or 4 or 5 or more remote calls necessary. So what's the impact on throughput? This is the results, the ZooKeeper result of the regular queue. The first thing we will learn is that we need a bigger scale. Because due to the fact that there are no retries, due to the fact that remove operations on a non-empty queue always succeed, we have a success rate of 100% for the remove operations, and this allows the extension-based queue implementation to achieve above 14,000 elements per second, which is a factor faster or more throughput by a factor of 17. Now, a few words on implementation. What we did was we took 2 existing coordination services, ZooKeeper and DepSpace, which are quite different in that they use different data models, they provide different synchronization primitives, they offer different fault tolerance guarantees, one is crash tolerant, one is Byzantine fault tolerant, they use entirely different replication approaches, primary backup replication in ZooKeeper, state machine replication, Byzantine fault tolerant state machine replication in DepSpace. And we made them extensible. So we had 2 services, Extensible ZooKeeper and Extensible DepSpace. Now, during the implementation work, we basically faced 2 challenges. The first thing was we did not want to add new functions to the kernel because it would make it larger. So the kernel should, in terms of the set of functions it provides, it should stay the same and still provide extensibility. The second challenge was with regard to server stability. We want to limit the damage an extension can do. For example, if an extension is poorly implemented and it crashes at some point, it should not bring down the entire service. So how did we do this? In order to make a coordination service extensible, what we do is we introduce a new component, the extension manager, which is responsible for intercepting client requests, checking whether a request actually triggers an extension or not, If it does not trigger an extension, it is just executed as a regular operation. However, if it triggers an extension, the extension manager is also responsible for executing this extension. Now, usually, the extension manager is completely transparent to the client. There's no need for a client to interact with the extension manager. However, there are two exceptions, and these are extension registration and extension deregistration. So for these cases where a client actually needs to communicate with the extension manager, we've created a built-in extension which is hardwired into the service and which provides a special node. In the case of Extensible ZooKeeper, this is /em, through which a client is able to communicate with the extension manager. So for extension registration, for example, what the client does is it takes the source file of the extension, which contains the code to be executed when the extension is triggered, as well as some configuration information on when the extension should actually be triggered. So in the example I showed you, it would say, okay, for a node next, please, if the getData method is invoked, please trigger this extension. So the client takes the source file and creates a subnode of this /em node, just as like a regular node. So for the client, there is no difference. We don't need a separate method to actually register an extension. But due to the fact that we create a subnode of this /em node, this means that the built-in extension will be triggered and it will take care of actually registering the extension. For extension deregistration, basically the same thing, no additional method necessary. All the client needs to do is to delete the subnode it has created earlier, and the built-in extension will take care of removing the extension from the service. So with regard to service stability, what we did was we reminded ourselves of our kind of definition of an extension as a sequence of regular coordination service operations plus a little bit of glue code. And the idea is to enforce that an extension is actually that. So what we did was we took a whitelist approach where we just listed some elements an extension may consist of, and elements which are not on this list are not allowed in extension. So this whitelist contains, of course, the methods that are part of the coordination service API. This whitelist contains basic arithmetic, Boolean, string operations, some conditional statements, for each loops, and that's basically it. So an extension, there's no need for an extension to create threads, there's no need for an extension to access the network, there's no need for an extension to access devices, so extensions are not allowed to do this. And the way we're currently enforcing this in our prototypes is to use a combined approach, which is based on a custom Java class loader, which, for example, ensures that an extension is only allowed to load and use the classes that are on the whitelist. This, for example, prevents an extension from just calling system exit and shutting down the entire Java virtual machine. There are some things we do not catch with the class loader. For that, we have extension code analysis prior to the extension registration. And during the extension execution, the extension is executed inside a sandbox environment, which ensures that if the extension crashes, this crash is dealt with and it does not take down the entire service. Plus, the sandbox environment also allows us to monitor what an extension does to the service state and probably deny the extension access if it does something we don't want it to do. So we've seen earlier that an extension is a good means to efficiently improve the distributed queue. We've implemented additional coordination mechanisms, a shared counter, support for leader election, and a distributed barrier. I won't have time to get into all the details, so therefore just a summary of the evaluation results. The shared counter suffered from the same problem as the distributed queue. Also, it has problems with contention, which allowed the extension-based version to improve the throughput of the shared counter even more in this case by 20x and 38x in ZooKeeper and DepSpace respectively. In contrast, the other two coordination mechanisms, leader election and distributed barrier, did not suffer from concurrency issues. Here the problem is, the benefit of the extension is to reduce the number of remote calls a client needs to do something. And this reduction in remote calls, for example, leads to a lower latency for leader election of 4 in ZooKeeper and almost half in DepSpace, as well as savings in the amount of data a client needs to send to the coordination service for the distributed barrier by about 2/3. So, in conclusion, having a small coordination kernel is a good idea, but the problem is that as there is no one-fits-all coordination kernel, as clients have to implement more complex abstractions themselves, there is the potential or the danger of having ending up with inefficient implementations. Our approach to deal with this problem is to make coordination services extensible, which means the client is able to write custom operations, register them at the service, they are executed atomically there, and after the client is done, the registrations, the extensions will be removed from the service. So if you're interested in, please take a look at our website. The code of both Extensible ZooKeeper as well as Extensible DepSpace is available. That's the end of my talk. Thank you very much. I'm happy to take questions. Many people leaving?
Etienne Rivière, University of Neuchâtel. One of the very nice features in ZooKeeper is the ability to set watches on data. Is that something you support in one way or the other, or is it just not necessary in the model that you propose?
Sorry, did you ask about the watches?
Yeah.
Yeah, the watches is an example of an event extension. So we, as I said earlier, we have two types of extensions, event extensions and operation extensions. In ZooKeeper, an event extension would allow you to customize what a watch can do, or when a watch will be triggered. And this, for example, is a good means to improve the lead election coordination mechanism.
Thanks.
John Wilkes at Google. If I understand this right, it's basically a software engineering argument that by providing an extensible service framework platform thingy, you can make it easier for people to put together new implementations of their particular coordination framework or particular coordination protocol. I was wondering if you've done any side-by-side comparisons on things like line count or complexity or bug rate or anything like that against, let's say, a little library of stuff that you can just link with your particular coordination protocol if you want to do it that way and then deploy your own server.
Would the library be executed at the server?
It would be the server.
Would be the server. No, we did not do any comparison of those.
Okay, well, thank you very much.